Key terminology in linear programming. Welcome back, everyone. In our previous lesson, we explored the fascinating way we can take complex, real-world business scenarios, like managing a factory or a shop, and translate them into mathematical models. However, simply creating a model isn't enough to solve it. To approach these problems systematically and accurately, we need to master the formal language and the specific terminology used in linear programming. In this subsection, we are going to dive into the precise definitions of each component that makes up what we call a linear programming problem, or LPP. Understanding these terms is the foundation you'll need before we move on to identifying variables and building our functions. 1. Decision variables. Now that we've established how business scenarios can be turned into mathematical models, let's dive into our first key term, decision variables. Think of decision variables as the heart of the problem. They are the specific quantities that we are trying to find or determine in order to reach our goal. If you are the manager or the decision maker in a scenario, these are the unknowns that are actually within your control. You get to decide their values to achieve the best possible outcome. To be more precise, in a two-dimensional problem, we usually denote these variables as x and y. You will see these x and y appearing inside what we call the objective function, which we will discuss in the next slide. To make this concrete, let's look at a real-world example. Imagine you are running a factory that produces two different items, product A and product B. In this situation, you need to decide exactly how many units of product A to manufacture. Let's call that x, and how many units of product B to manufacture. Let's call that y. These values, x and y, are your decision variables. Once we determine the best values for x and y, we can move on to defining our goal, which is the objective function. 2. Linear objective function. Think about the purpose of any optimization problem. In the real world, we aren't just calculating numbers for the sake of it. We are trying to achieve a specific goal. Usually, that goal is to either maximize a benefit, such as increasing profit, or to minimize a cost, such as reducing total expenditure. To solve this mathematically, we express this goal as a specific function. Formally, we define the linear objective function as a linear function, which we denote as z equals a x plus by, where a and b are constants. Our task is to find the values of x and y that make z as large as possible or as small as possible. Now you might be wondering, why do we specifically call it linear? It is called linear because the variables x and y are only to the first power, meaning they are degree 1, and they are never multiplied by each other. If you saw an x squared or an x multiplied by y, it wouldn't be linear anymore. To make this crystal clear, let's look at a practical example. Imagine a shopkeeper who earns a profit of $50 on every table, which we'll call x, and $20 on every chair, which we'll call y. To build our objective function, we follow 3 simple steps. First, we identify the profit per unit. That is, $50 for a table and $20 for a chair. Second, we multiply that profit by the quantity produced, giving us 50x and 20y. Finally, we sum these together to get our total profit, which we represent as z. So, our objective function becomes z equals 50x plus 20y. Now that we've identified our decision variables, those unknowns we are trying to solve for, let's move on to the second key component, the linear objective function. As we move to the next slide, keep this function in mind, because while this function tells us our goal, the next concept, the constraints, will tell us the limits we have to work within. 3 constraints. Now that we have identified our decision variables, those unknowns we are trying to solve for, and our objective function, we need to talk about the reality of the situation. In the real world, we can't just produce an infinite amount of goods to make infinite profit. We are always limited by resources, such as time, money, raw materials, or even physical space. In mathematics, we refer to these limitations as constraints. To be precise, constraints are the linear inequalities or linear equations that restrict the possible values our decision variables can take. there is one very important type of constraint you must always remember, which we call non-negative constraints. Think about it. In a physical problem, you cannot produce a negative number of items. You certainly can't produce -5 chairs. Because of this, we almost always include constraints stating that x is greater than or equal to 0, and y is greater than or equal to 0. Let's look at a practical example to see how we translate a real-world limit into a mathematical inequality. Suppose a carpenter is working and has a total of 100 units of wood available. To make a table, which is one of our decision variables, we need 10 units of wood. For a chair, which is our second decision variable, we need 2 units. To build the constraint, we follow 3 simple steps. First, we calculate the wood used for tables, which is 10 times x. Second, we calculate the wood used for chairs, which is 2 times y. Finally, since the total wood used cannot exceed our limit of 100, we combine them into a single inequality. 10x plus 2y is less than or equal to 100. This inequality is a constraint, and it works alongside our objective function to define the boundaries of our optimization problem, which we will define in the next slide. For optimization problem. Now, before we move on to the formal definition of a linear programming problem, I want us to step back and look at a much broader mathematical concept called optimization. Think of it this way. In our previous slides, we talked about goals like maximizing profit and limitations like resource scarcity. Optimization is simply the mathematical umbrella that covers all of these scenarios. By definition, an optimization problem is any mathematical challenge where we are searching for the absolute best possible value, either the maximum or the minimum, of a specific function, which we call the objective function. However, we aren't just searching blindly. This search is always performed subject to a set of given restrictions, which we've already learned to call constraints. To make this more concrete, let's look at a real-world example outside of a factory or a shop. Imagine you are planning a road trip between 2 cities. You want to find the shortest possible route to minimize your fuel consumption. In this scenario, your goal is to minimize fuel, and your constraints might be things like road closures or speed limits. Because you are seeking the minimum value of a function under specific restrictions, you are solving an optimization problem. In the next slide, you'll see how we specifically categorize these types of problems when everything involved is linear. 5. Linear programming problem, LPP. In the previous slide, we discussed the concept of an optimization problem, which is any problem where we seek a maximum or minimum value under certain restrictions. Now, look closely at what happens when we add one specific condition. If both our objective function and all our constraints are strictly linear, then this optimization problem takes on a specific name. We call it a linear programming problem, or LPP for short. To put it formally, a linear programming problem is a specific type of optimization problem where the objective function is linear, and every single constraint is expressed as either a linear inequality or a linear equation. Essentially, if there are no exponents or variables multiplied by each other in your formulas, you are officially working within the realm of linear programming. Now that we have defined our individual components, the decision variables, the objective function, and the constraints, it is time to bring them all together to define our main topic. Summary example, putting it all together. Now that we have gone through all the individual definitions, let's bring everything together in a single, practical scenario to see how these components interact. Imagine you are running a bakery. In this business, you really produce 2 main items, cakes and cookies. First, let's identify our decision variables. As we discussed in the second slide, these are the unknowns we need to determine. Here, our decision variables are x, representing the number of cakes produced, and y, representing the number of cookies produced. Next, let's look at our goal, which is our objective function. Suppose you earn a profit of $100 for every cake and $30 for every cookie. Our goal is to maximize our total profit, which we will call z mathematically. We express this as z equals 100x plus 30y. However, as we learned in the section on constraints, we cannot produce infinite amounts of goods because we are limited by our resources. We have two main restrictions here. First, we have a flour limit. The amount of flour used for cakes and cookies cannot exceed 20 units. This is written as 2x plus 1y is less than or equal to 20. Second, we have limited oven space. The total number of cakes and cookies combined cannot exceed 12. This is expressed as x plus y is less than or equal to 12. And, as a reminder from our previous slide, we must also include our non-negativity constraints, meaning x is greater than or equal to 0 and y is greater than or equal to 0, because we simply cannot bake a negative number of cakes. Now, take a look at the structure of this entire model. Because our profit formula is a first-degree equation and all our resource limits are expressed as linear inequalities, we can officially classify this entire setup as a linear programming problem. In the next slide, we will quickly recap these key takeaways to ensure you have the core concepts down. Key takeaways. First, remember that our decision variables are simply the unknowns that we are trying to find the value for, which we usually represent as x, and y. Think of these as the quantities you have control over. Second, we have the objective function, which we denote as z. This is the mathematical formula that represents your ultimate goal. It is the specific equation that you are either trying to maximize, such as profit, or minimize, such as cost. Third, we must account for the constraints. These are the rules or the boundaries of your problem, expressed as linear inequalities. They represent the real-world limitations, like limited time or raw materials, that prevent you from having infinite resources. Finally, when you bring all these pieces together, where both your goal and your limitations are all expressed in linear terms, you have what we call a linear programming problem, or LPP. All right, let's take a moment to recap everything we have covered in this lesson so that you have a clear mental map of these concepts. Now that we have the definitions down, let's look at some common pitfalls to watch out for in your upcoming practice problems. Common mistakes to avoid. First, be very careful not to confuse your objective function with your constraints. It sounds simple, but it's easy to mix them up when you're reading a long word problem. Just remember this distinction. The objective function is your ultimate goal. It is what you are trying to achieve, whether that is maximizing profit or minimizing cost. On the other hand, the constraints are the rules or the boundaries that limit you, such as your limited supply of raw materials or time. Second, a very frequent mistake is forgetting the non-negativity constraints. When you are writing down your mathematical model, don't just stop after the inequalities for your resources. You must always include x is greater than or equal to 0 and y is greater than or equal to 0. In the real-world scenarios we've discussed, like producing chairs or cakes, it is physically impossible to have a negative quantity. Always include these to ensure your model is logically sound. Finally, keep a close eye on the linear part of linear programming. You must ensure that your variables are not squared, such as x squared, and they should not be multiplied by each other, such as x times y if you see any variables raised to a power other than 1, or if variables are being multiplied together, then the problem is no longer a linear programming problem. Now, as we wrap up our session, I want to highlight a few common pitfalls that students often encounter when working with linear programming. Paying attention to these will help you avoid losing marks in your exams. If you can avoid these 3 mistakes, you will have a much stronger foundation for solving complex optimization problems.